Applications of derivatives. The surge function. So, in medicine, we often want to measure how people metabolize certain medicines and drugs in their bloodstream. One way we do this is by using a model called the surge function. The surge function measures how much of a drug or medicine is in the person's bloodstream at a given time. Surge functions have the form AT e to the bt. Now, surge functions can be used to predict when you can need another dose of medicine. It can be used to predict how high the concentration will go, and data is often used to determine when to give second doses of certain medicines based on the qualities of the surge function for the particular medicine. You can see that this function has the variable in two places, both in the front and in the power of e. Let's take a look at the picture so we can talk about how the surge function behaves. All surge functions have the same general shape. At time equals 0, if you were to draw the patient's blood, there would be zero trace of the medicine in the blood because it takes a few minutes to start showing up. Then over time, the amount of drug in the bloodstream starts to increase. It doesn't increase indefinitely. Instead, it goes until it reaches its maximum concentration, and then it slowly dissipates back out of the body. So all surge functions have this general shape, and depending on your value of b, will dictate how quickly you hit the maximum of this function. So there's two important points here that we're really interested in. And those 2 points are the global maximum and the inflection point. So notice here that we have an inflection point. To the left of the inflection point, we're concave down. To the right of the inflection point, we're concave up. Which means that once we get to the inflection point, the rate at which the drug is leaving the body starts to slow down. Generally, the inflection point is when it's safe to take another dose of whatever your medicine is. So we want a good way to be able to solve for the maximum and the inflection point of this function. Now we have all the tools we need to do that because we know how to find maximums and inflection points using our derivatives. So let's see how this works. Global maximum and the inflection point of a surge function. So remember, our general form was C of t equals AT e to the bt. So if we want to talk about the global maximum, we're looking for the critical point of this function. We know from our picture that there's only one. So if we can solve for the critical point, we know that that's it, the global maximum. So here, when we want to take the derivative of this function, notice that we're going to have to do a product rule. So the first function is AT, and the second function is e to the bt. To get the derivative of AT, we remember that a is a constant, so the derivative is just a. So to get the derivative of e to the bt, we have to do a chain rule. So z will be bt, and dz dt will be the derivative of that, which is b. Using the chain rule, that means that my g prime is be to the bt. So now, putting that all together, we get that the first derivative of a surge function is a e to the bt plus b e to the bt times at. And we want to know, is there a way to figure out when that equals 0? And the answer is yes. So if we're careful with our algebra, we'll be able to figure this out. Notice that both terms have an a and an e to the bt. So we're going to factor that out. So if we take out an a e to the bt, I'm left with a 1 from the first term and a bt from the second term. Now, if you remember from algebra, e terms will never ever equal 0, which means that what's left in the parentheses will have to be what equals our 0. So 1 plus bt has to equal 0. So that means 1 equals negative bt, and t equals negative 1 over b. So the global maximum of this function is going to happen at time negative 1 over b. So that's really interesting because that means we can just take the power from our surge function and do -1 divided by that power, and that will tell us when the global maximum happens. Remember, global maximums and minimums are defined by their dependent value. So if we want to know what the actual concentration is at that point, we'd have to plug that value back into our concentration function to get the corresponding y value. We can do a similar calculation to figure out where our inflection point is. Remember, that in order to find our inflection point, we're going to start by finding where the second derivative equals 0. So to get the second derivative, we go back to the unfactored form of the first derivative, and we see if we can take the derivative of any of the pieces. So for the first term, ae to the bt, we only see the variable one time, and that's up in the power, which means that we can take the derivative of this function using a chain rule. So for that particular first function, we'll use that z equals bt and dz dt equals b. So that means that my first term has a derivative of ab e to the bt. Now my second term is be to the bt times at. So I'm going to have to use a product rule there because again, now I see the t in two places. So for my product rule, my f I will do as be to the bt and my g will be at. So the derivative of g will be a, and the derivative of be to the bt is going to be a chain rule with z equal to bt. Well, I know from before that if z equals bt, that dz dt is b, so another b comes out, and I get b squared e to the bt. So plugging that into my product rule, I'm going to have f prime times g, so b squared e to the bt times at plus f times g prime, so b e to the bt times a. Now I want you to look at the first and third term because those are the same term. The order at which our elements are presented are different. So in the first term we have a times b times e to the bt. But in the third term we have those same things. We have an a, we have a b, and we have an e to the bt. So that means they're the same. And so therefore I can write that as 2ab e to the bt plus b squared e to the bt times at. So I've combined the first and third term. And again, I want to know when does that equal 0. And so here again, I want to factor out the things that these have in common. So again, they have an a e to the bt in common. So a e to the bt. From the first term, I'm left with a 2b plus, from the second term, I'm left with a b squared t equals 0. So like before, I remember that e can never be equal to 0, so I have 2b plus b squared t equals 0. Solving for t, I'm going to bring this term over and then divide, and I'm going to get t equals negative 2b over b squared, but one of the b's will cancel, and I get negative 2 over b. So again, that means I can look at my original surge function, figure out what my b is, and do negative 2 divided by b, and that will tell me where my inflection point is. So now that I've done out all the work for the first derivative and the second derivative to identify where the global max and where the inflection point happen, I'm able to come up with formulas that I can use to identify them quickly and efficiently for various surge functions. So let's see how I can take these two formulas and use them in action. Example 1. The amount of a particular drug in the bloodstream is measured by C of t equals 5t e to the negative 0.25t measured in milligrams and time t measured in hours since the drug has been administered. What is the maximum concentration this drug reaches? So if we're talking about maximums, let's remember what surge functions look like and what we know. So surge functions look roughly like this. And we know the maximum, we said, happens at -1 over b. So we need to identify what our b is here, the rate up in the power of e. So for this particular model, my b is -0.25. So -1 over -0.25 gives me 4. So the maximum concentration happens at time equals 4. However, we want to know what the maximum concentration is. So what we need to do is we need to take when that happens and plug that into the surge function. So I have 5 times 4 e to the -0.25 times 4. If I plug all those numbers in carefully, I'm going to get 7.36. So I'm rounding to 2 decimals, but of course you'll round however the problem tells you to, or to 2 decimals if you're not told otherwise. So 7.36 milligrams is the highest measurement that we're going to get for this surge function. And again, that's the maximum concentration that I reach. So that is going to be here, 7.36. If we had been asked about the inflection point, we know the inflection point is 2 over b. So we would know that that happens at time equals 8. So being able to figure out where we reach the maximum and inflection point was a matter of using the product rule a few times. Of course, if you don't remember the shortcut, -1 over b and -2 over b, you can always use the product rule to again find out where we're going to hit our maximum. Let's see what else we know about surge functions. Example 2. The concentration in Ng over ml of a particular type of medicine in the bloodstream is given in the graph below as a function of time t in hours. If the minimum effective concentration is 10 Ng per ml, at approximately what time does the effect of this medicine wear off? So, minimum effective concentration means that if you have some sort of pain or some sort of problem, you need to have a certain amount concentrated in your blood of this painkiller or drug before you feel the effects. So that's called the minimum effective concentration. So once you've passed that threshold, then your pain has been taken away and you're feeling good, or at least less in pain for some time. But eventually, the amount of the drug in your bloodstream will dip back below that effective concentration because it doesn't stay in your blood forever. So this problem examines how we determine when this drug is effective. So if the concentration is 10, we want to graph 10 against our surge function. So we have a picture of our surge function here. And so if we're talking about the minimum effective concentration, we're talking about the time that we're above 10, because that's when there's enough of this drug in your blood to have some sort of effect. So the minimum concentration starts right here around 1. So at time equals 1, that means after 1 hour, you're finally at the point where you're getting some relief or you can feel the effects of this drug. However, this question asks when it's going to wear off. So that means we want to know when we fall below the minimum effective concentration. So we come to our other endpoint and we look at where this is going to happen. And that happens at approximately time equals 10 hours. So here, after 10 hours, the effects of this medicine wears off. Now, a word of caution. If you don't have a picture already graphed of your surge function, then you're going to need to do this on a calculator or some sort of computer, because you cannot set a surge function equal to a constant and algebraically solve. That's not something we have the tools to do, which means the only way we can look at minimum effective concentration is by graphing the surge function and graphing y equals the minimum concentration to see where they intersect.